All right. Okay. Okay. So everyone, today we will begin with the MOSFET operation. Okay. Last week we have completed the MOSFET fundamental. Okay. The basic structure of MOS capacitance. Okay. MOS capacitance. That time we looked on the N channel and the P type and N type of MOSCAP. Okay. So today on the MOSFET operation. Okay, of course, here there will be two type, okay, P channel and N channel, okay. The IV characteristic, I think you all still remember how it looks like, the device structure of MOSFET and also the IV characteristic. Okay, so second. Okay, so there will be introduce the MOSFET structure. Okay, I think you have familiar with it, where it has the basic structure is where it has the gate. Okay, if you still remember, you have done in the microelectronics lab. Okay, all right. So this is the gate. Okay, the source and also the drain. Okay, if you still remember, in the bit underneath the gate there is a dielectric layer. Okay, usually silicon dioxide. Okay, and then you have here is the substrate. Okay, substrate. Okay, so there will be two types of the MOSFET structure. It could be the N channel. Okay, the N channel. Okay, and also the P channel. Okay, current voltage relationship, if you still remember, this is the current, okay, in linear plot. Okay, in linear plot mean when you apply voltage, okay, this is VGS voltage, this is drain current. Okay, when you apply voltage, there will be apply voltage reach the threshold voltage, if you still remember, and then the current start increasing. So this is in linear plot. Okay, in log plot, there will be like this. Okay, I think you also plot the log plot during the laboratory. Okay, so you're gonna have something like this behavior. Okay, if you still remember, right? Okay, and then the transconductance. Okay, in MOSCAP, we look on the capacitance characteristic. Okay, in here inside, when there is a channel, okay, when there is a channel, electron flow underneath the gate. Okay, the other parameter that is also important is the resistivity. Okay, so in here they going to explain on the transconductance. Okay, transconductance is the 1 over resistance. Okay, how is the resistivity characteristic in the channel. Okay, and then the substrate bias effect. Okay, usually so this is the bulk. Okay, if you still remember, bulk or substrate are the same thing. Okay, usually bulk we didn't connect to any voltage application. Okay, however, now we will look through about what happened if we apply bias to apply VBS or VSB greater than 0. Okay, usually we ignore the bulk. It's either we didn't connect to anything or it is usually grounded. Okay, now what happened if we apply bias to the substrate or the bulk? Okay, all right, and then the frequency limitation. Okay, finally. All right, so this is the FET Organization Chart. Okay, so previously FET has been known as the JFET, okay, Junction Field Effect Transistor. Okay, during this time, of course, it has two type of channel, P channel and N channel. All right, and then now we have MOSFET. Okay, I think you still remember it has two type of MOSFET, D MOSFET and E MOSFET. So D represent as a depletion MOSFET. Okay, depletion. Okay, and E then is enhancement MOSFET. Okay, enhancement MOSFET. Of course, it has two type, N channel and P channel for both type of MOSFET. Okay, finally the CMOS, which is the combination the combination of PMOS or P channel and N channel. All right, so this is the basic structure of the N channel enhancement mode MOSFET. So this is the E MOSFET, N channel E MOSFET. Okay. Why N channel? Because at the channel there, it is the at source and drain. Okay, it is the concentration is N plus, which is heavily doped N type. Okay, and you have the gate. Okay, you have source and you have the drain. Okay, same like I have shown you just now. So this shaded area over here. So this is the oxide. Okay, or silicon dioxide. Okay, or you in other name also, it is known as the dielectric layer. Okay, dielectric layer. All right, so for this E MOSFET, okay, initially there is so since this is N channel MOSFET, so N channel, okay, from the name itself, inside the channel the majority carrier are electrons. Can you wait for a while? Who's that? Wait, can you wait? Sorry, got someone knock, but nobody there. Okay, so N channel. Hello, can you hear me? I'm back.
Yes, madam.
All right, okay. So from the name itself, N channel means the majority carries are electrons. Okay, therefore, this is the channel. Okay, this is the channel, and inside this channel is the electrons. Okay, the majority carriers of electron. Okay, like I said previously, substrates or body or bulk are the same thing. Usually it is grounded. Okay, usually this is equal to 0, but in this topic we're going to look through what happened if VSB greater than 0. What happened to here? Okay, this is the symbol. Okay, for this is VG, and the current flowing here is ID. Okay, usually VB is equal to 0. All right, so this is the structure and also the symbol. All right, so for the biasing operation, okay, what happened when you be apply bias? Okay, so usually this is what happened. Okay, so in here looks the character um, the, the structure of a MOSFET. Okay, so what happens? So this is initially the E MOSFET. Okay, there is no channel in between source and drain. Okay, so this is this drain and source. Okay, okay, now what happened if we apply the gate voltage? Okay, gate voltage. Okay, initially there is no channel because now there is no voltage application. Okay, no voltage application, or there is no channel because the VGS now is less than not less than 0, less than the threshold voltage. Okay, there is no channel. Okay, however, if we apply a voltage, okay, the VG is increasing. Okay, VGS now greater than 0. Okay, and also VGS greater than the V threshold. All right, so what happened here? So there will be Since this is P substrate, okay, P substrate. Okay, so and here the positive voltage, okay, will attract the minority carrier of electron over here. So electron will be accumulated at this region underneath the gate, okay, and therefore there will be channel created. So this is the induced channel. Okay, when there is a channel, okay, so the electrons start flowing from source to the drain. Okay, a lot of electron over here. Okay, then only you can measure your current ID. Okay, so this is how the MOSFET characteristic looks like. Okay, so this is the IV characteristic. So for example, this is your drain current. Okay, this is your VG. Okay, 0 volt. When you apply VG greater than the threshold voltage, okay, then channel will be induced underneath the gate. Okay, and as you increase further, okay, the gate voltage, okay, current starts because channel will be much greater, bigger, and current will start increasing. Okay, so as you can see from here, current is increase, okay, as the VGS increase. Okay, so in this case, this is what we call it as a enhancement mode. Okay, enhancement mode, right? Enhancement mode and channel. Okay, where it been enhanced, or the channel is with application of VGS. Okay, in this case, the current flow from source to drain. Okay, so this is your current voltage characteristic. Okay, I think you have familiar with this before. Okay, so this is the basic structure of a D type, or the depletion MOSFET. Okay, D MOSFET. Okay, so if you look the different, okay, so this is E MOSFET. Okay, E MOSFET. Okay, initially, okay, there is no channel created. Okay, you only can apply voltage. Okay, there will be a channel created lah if you apply voltage. Okay, however, for the MOSFET, okay, there is already channel induced. Okay, there is already channel induced here. Okay, so this is the channel. Okay, at initial condition, there is channel induced. Okay, as you can see also from the symbol. Okay, from the symbol, okay, it is a straight line. Okay, it is a straight line. However, from the E MOSFET, it is a dotted line because there is no channel at initial state. All right. So this is more like the MOSFET. Okay, at initial state there is a channel induced. Okay, meaning that there is a small current portion. Okay, even though we didn't apply the voltage. Okay, let's look at the characteristic over here. So this is N-channel D MOSFET biasing operation. So in this case, okay, it can be operated in depletion mode. It can also be operated in enhancement mode. All right. So if you look at the first case, okay, okay, this one, when VGS equal to 0, okay, there is already a channel induced over here. So this is the channel initial channel. Okay, so at VGS equal to 0. Okay, of course, when there is a channel, okay, there is a small portion of electrons. Okay, small portion of electrons over here that is flowing through. Okay, due to this electron, then you can get the current. So there is a current, small portion of current exists at VGS equal to 0. So what current is this? So in this case, for example, the starting point of the current is 5 milliampere. So this starting point of current is known as the IDSS. Okay, if you still remember, IDSS is the IDSS is the in the specification sheet of the depletion MOSFET. So there is a value lah for the IDSS. Okay, in this case, if you look at the ID VGS, so this is the ID VGS. So there is the VGS equal to 0. Okay, in this case, okay, VGS equal to 0. There is a small portion of current ID which is equal to IDSS. All right, so what happened when we apply greater voltage? So what happened when we apply VGS negative? So VGS less than 0. Okay, so at this point, so this is negative. Okay, negative. Okay, so in this case, so this negative, okay, negative terminal will be able to attract the holes, okay, from this p-type substrate. Okay, okay, there will be a hole accumulated over here. Okay, so in this region, okay, there will be a hole accumulated here, and also in this case, current is reduced because of hole accumulated over here. Okay, current from instead of electrons, so at this region, this is the hole. Okay, holes. Okay, due to this, current ID will start decreasing. Okay, why? Because of the concentration of holes, and the holes current is much smaller. So due to this, current is decreasing. Okay, current is decreasing until it reached the negative VGS off, until it's turned off. Okay, so this is the depletion mode. Okay, for this D MOSFET. Okay, it has two characteristic or two modes. Okay, depletion mode. So this is for the case of depletion modes. Okay, so now what happened when we apply VGS? Okay, greater than 0. Okay, so what happened when we apply VGS over here greater than 0? So in this case, okay, this plate will be much positive, so it will be able to attract the electrons. Okay, electrons, okay, will be accumulated here, and channel induced, okay, channel will be much bigger. Okay, in this case, current is increasing. Okay, increasing. In this case, 7.4 milliampere. So due to this, current is increasing. Right, as you can see that D MOSFET is behave two mode of operation. Okay, the left side is the depletion mode. Okay, the right side is the enhancement mode. All right. Okay. Okay, so this is for the D MOSFET. Okay, all right. So if we move forward, okay. However, here in this chapter, okay, we're going to look through on the E MOSFET. Right. So for this case, okay, E MOSFET, it is a E MOSFET, enhancement MOSFET. Right, so what happened when we apply VGS less than the threshold voltage? Okay, for example, in this case, VGS still equal to 0. Okay, so there will be no channel induced. Okay, no channel. Okay, no channel. And also current here, we may assume that current is equal to 0, right? No channel, and drain to substrate bias is in reverse bias. All right, so what happened here means that this MOSFET is in off state condition. Okay, so what happened when we apply VGS greater than 0? Also greater than the threshold voltage. Okay, so in here it is expected that this portion, okay, the positive plate over here will be able to attract the electrons. Okay, so these electrons, okay, is uh, will be flowing in the beanstalk centric. Okay, and due to this, okay, due to this, channel will be induced. Okay, then channel induced, or in other name, it is named as the inversion layer. Okay, due to the channel induced, okay, due to this, current is actually increasing. So now you can measure the current. Current now is greater than 0. So current start flowing in this term, okay, where VGS greater than 0 and VGS greater than the threshold voltage. Okay, so this is what happened for the IV characteristic. Okay, so now with the same structure, okay, with this same structure, the channel induced, okay, at the right side with the channel induced. So now we want to look at the characteristic, IV characteristic in terms of the transconductance, okay. All right, so if you look at here, okay, in here, so this is the bulk, okay, with the same position where VGS greater than 0 and greater than the threshold voltage, okay. So in here, there is the electrons flowing, okay. However, in this case, VB or the VSB in this case equal to 0, okay. So the bulk is 0, which is grounded. All right. So if you look at here, if we increase the drain voltage, okay, this is the characteristic. So the right side is the characteristic of drain current versus VDS. Okay, as you increase the VDS, much greater than 0. So this is the characteristic. Okay, if you look at if you have VGS less than VT, there's no point because the current still equal to 0. Okay. However, when you apply VGS greater than the threshold voltage, so what is the current characteristic versus VDS? Okay. As you further increase the VDS, okay, the current start increasing. Okay. So this is the characteristic inside the channel. Okay. Inside the channel. So what happened here? So inside the channel, there is the slope of this curve, which is IDVD. So this slope is actually known as the resistance. Okay, this resistance, the slope over here, which is equal to the resistivity inside the channel. So this slope is equal to the RDS, okay, the resistivity inside the channel. Okay, so when you have the resistivity, okay, of course there is a parameter in Niemann that shows about the transconductance. Okay, due to this you have transconductance. Okay, GD is equal to the 1 over R, right? So the current flow over here, which is equal to I equal to GD VDS, or in other words, it is actually I is equal to the VDS. Oh, sorry. VDS over RDS. Okay, over RDS. So RDS is the slope. All right. So what happened when we look at here? So what happened when VDS start increasing, okay, much greater than the 0. Okay, when this VDS much greater than 0, for those uh, you cannot if you still remember, okay, you are in your lab, okay, you voltage, okay, you apply this is your current voltage characteristic. For example, you have VGS and then you have ID. If you still remember, you have this characteristic and also you have this characteristic. Okay, so this one when you apply VDS1, and this is when you apply VDS2. If you still remember, okay, you got two characteristic. Okay, why you get two characteristic? Because you apply two different VDS voltage. Okay, so larger VDS and lower VDS. Okay, for if you still remember, you apply VDS 0.0 volt, and you also apply VDS if I'm not mistaken 1 volt. Okay, so this one is during linear. Okay, linear. Okay, so when you apply less VDS, so this is during linear. Okay, when you apply greater VDS, so this is during saturation, if you still remember. All right, so what happens when we apply at saturation? VDS much greater than 0. So this portion actually will become the portion underneath the drain, okay, will actually be extended, okay, because we apply voltage greater. So this region will be extended. Okay, so this is plus, okay, much greater. Then it will attract more electrons from this p type, and this region it will be extended further. Okay, region underneath the drain, okay, will be extended further if you apply greater drain voltage. All right. Okay, so in this case, that's why when you apply VGS greater than VDS, that's why when you apply VDS greater, the characteristic is increasing. Okay, so current over here will be much increase. Why? Because this positive, okay, this positive will actually create an extended region over here. Okay, why? Because it able to attract more electrons from the p type. Okay, more electron from the p type, and that's why ID is increasing. Okay, if you still remember that, okay, you apply two at linear region and saturation region. All right, so this W, okay, like I said, W or the resistance inside the channel, okay, okay, the resistance inside the channel, which is RDS, so the slope over here. All right, so this transconductance or the channel conductance, okay, not only depends on the I want to change color. Wait. Okay, so not only depends on the L, okay, if you still remember, so this is L, the channel length. Okay, however, when you fabricate your MOSFET, it also has the W, okay, the W, okay, with this, which is the width, okay, the width, okay, so this is the W, okay, the W. Okay, so the transconductance, okay, or the resistivity inside the channel, okay, not only depend on L, it also depend on the width, okay, and also the mu. So this is the mobility of electron. Okay, mu n is equal to the mobility of electron, which is equal to how fast these electrons can flow inside the channel. So how mobile this electron inside the channel can flow from source to the drain. So that is the mu n, or the mobility. Okay, and Q, of course, you all know. So Q is represented as the total charge inside the channel. Okay, total charge inside the channel. So the transconductance equal to W over L mu n times the total charge in channel. Okay, so this is what happened for the IV. All right, so if we look forward, okay, so since I don't know whether you still remember or not in your class or so on, in your lab, okay, especially in your lab, okay, I don't know whether you still remember or not. However, this is important, okay. Okay, so the operational of N Mosfet. So this is the characteristics. So what has been taught previously, the IDV characteristic. So ID versus gate voltage. Okay, you apply gate voltage greater than the threshold voltage. Okay, the current start increasing. So what happened when you look at the ID-VD characteristic? If you still remember, so this is ID-VD characteristic. Okay, there will be several. There will be four steps. Okay, to see the characteristic of ID-VDS. Okay, the first one, when you apply small VDS, so this VDS is small VDS. All right. So of course, in this case, VGS greater than 0 and VGS greater than threshold voltage. Okay. This is the structure. The oxide, if you look at the um, this is the gate, oxide, and drain. Okay, so when you apply VGS greater than 0, VGS greater than the threshold voltage, the channel will be induced. So the blue shaded, the blue area here is the channel induced. Okay, of course, there will be a current flowing. Okay, as you can see here. So VDS at this point, so current increase. Okay, current increase. Okay, as you increase the VDS, current start increase. Okay, however, when you apply you increase more the VDS. Okay, you increase more the VDS. So this VDS will be increased further. Okay, and you apply VGS greater than 0. Of course, in this case, VGS the same greater than the threshold voltage. Okay, in this case, okay, the voltage across here, okay, this one will be, if you look at here, the channel at this region underneath the um drain, okay, will be reduced. Okay, will be reduced. All right. So due to this, okay, the voltage near the drain will also drop. Okay, the voltage near the drain will also drop. Okay, there is a current, drain current. However, the current will be slowly. Okay, the current, it will be slowly reduced. Okay, slowly reduced. As you can see, this characteristic is from you apply VDS. However, if you apply greater VDS, okay, so current start increase, but however much slower. Okay, much slower. Okay, so is the characteristic. So what happens when we further increase? Okay, of course, in MOSFET it has the VDS saturation point. Okay, so what happens when you apply VDS? Okay, that reach the VDS saturation. Okay, so what happened here? If you look at here, so you apply VGS greater than 0, VGS greater than the threshold voltage. Okay, so now VDS is equal to the VD saturation. Okay, is VS equation. So in here, channel or the voltage here will actually drop. Okay, will actually drop. In this case, this region will become much smaller. Okay, so when this region become much smaller, and current increase in a slow motion. Okay, same like the previous one. Okay, still increasing because the VDS increase. However, and if when it reach the VDS saturation, it will stop. Okay. Now, what happens when we apply VD greater than the VDS saturation that it's supposed to be? Okay, so this one, VDS greater than the VDS saturation. So what happened over here? So this region will become pinch off. Okay, pinch off. The region underneath the drain will become pinch off. Okay, due to this, okay, current just now that is increased slowly. However, this current, because of this pinch off, current will saturate. Okay, current will saturate. As you look at here, it is slowly increased as you apply until it reach the VDS saturation. However, when you apply VDS greater than the VDS saturation, so current will saturate. Okay, so this is the characteristic of ID versus VDS. Okay, if you still remember, you also simulate ID VD. Okay, you also simulate ID VD. Okay, not only ID VG. Okay, during your simulation, you also simulate ID versus VDS. Okay, so this is the characteristic why it get this kind of characteristic. Okay, so ID start increase until it reach saturation. So this is for the case of ID VDS. Okay, for those who do devices, you should know how it works. Okay, for the ID versus VDS. Okay, in this case, due to the pinch off, voltage underneath the drain will be 0. All right, so this is what you simulated, if you still remember. So this is the current, okay, current increase until it reach the saturation, and then it will saturate. So this is for different VGS, okay, for different VGS. As you increase further VGS, current ID is increased. Okay, so this dotted point is actually the saturation, the VDS saturation. So VDS saturation is equal to the VGS over. This case, it has two. What can I say? It has two type or two mode. Okay, the right one is the saturation region. Okay, the right one is the non-saturation region. All right, so the ID characteristic, okay, for the non-saturation region, this is normal ID characteristic, okay, so I think you have seen this previously during the lab, um, uh, during during uh, electronic
SI.
device, if I'm not mistaken. Yeah. During electronic device. Okay. So I is the 2L mu n ox. VLSI also you see this current voltage E is equal to K. K is the constant VGS over VT square. And for the saturation ID equal to K and VGS minus VT square. So this is depends on the parameter K, W, and L, and also the length. All right. Okay. All right. So this is the example. Okay. Quite simple lah. The example, I think for MOSFET, the calculation is, I think for all calculation will be no problem for you. More on the explanation and drawing energy band diagram will take some time for you lah. Okay. So design okay, basically this question. Okay, given the length is equal to 1.52 micrometer, mu, okay, or the mobility is equal to this value, Cox, blah, 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 ID saturation also given, okay, you just have to use the ID set equation, okay, ID saturation, which is from, okay, so ID saturation is equal to this equation. Okay, now you want to find W, so more plug in all the value. So finally you will get W 11.8 micrometer. Okay, this is quite straightforward. Okay, so let's take a look on the P channel. So P channel MOSFET, it is vice versa from the N channel. If N channel you apply, okay, N channel you apply a positive voltage, okay, VGS greater than 0. For P channel you apply VGS less than 0, because you want to track the holes, okay, holes inside here, okay, holes. Oops. Okay, so the current characteristic, of course, instead of Kn due to the electron, now you have Kp due to the holes. Okay, so basically the equation is quite the same. It's only that the terms now is instead of N, now it become P. Okay, represent for holes. All right. Okay, so the transconductance, okay, transconductance is actually the slope over the slope for IDVDS, okay, GM is equal to 1 over R, so M is equal to V, so this is the anti-slope of this IV characteristic just now, so this is VDS and this is ID, so this is anti-slope lah, so this is the R. Okay, so GM also equal to ID over VG. Okay, so since you have Vg mu W mu n C ox over L times VDS, and finally you have two equation for transconductance at non-saturation region and transconductance at saturation region. Okay, nothing much. Okay, so this is what I said now. Okay, previously bulk equal to 0. Okay, from what you have learned, okay, the bulk is always equal to 0. Okay, now we want to look what happens when we apply bulk or substrate greater than 0. Okay, instead of to the substrate. All right. So this is how it looks like. Okay, of course you have to know the energy band diagram. All right. So this is what happened. Okay, usually this one we apply equal to 0. Okay, now we want to look what happened when we apply bulk greater than 0. So what happened here? Okay, so of course VGS this case greater than 0, and also VGS greater than the threshold voltage. Okay, it able to attract electron, the majority carry electron from the p substrate and so on. So this region will be created. So this is the channel induced. Okay, channel induced. Okay, so this is the VDS. Okay, VDS. So when you apply VDS greater than 0, so what happened? So basically you apply VDS greater than 0, and sometimes you apply much greater because it has two types, linear region and saturation region. Okay, so in this case VSB equal to 0. Okay, so what happened? VSB equal to 0. So the first one here, VSB is equal to 0. So the same energy band diagram, okay, there will be a bending over here. Okay, there will be a bending over here, and there is a depletion mode. Depletion region, which is represented as XD, if you still remember, and also at equilibrium. Okay, at equilibrium, the phi S is equal to the double phi FP equal to threshold voltage, if you still remember. So this is normal mode when VSB is equal to 0. Okay, so nothing new here. Okay, so electron at inversion layer has higher potential, and at equilibrium the phi S equal to twice phi FP, and this Niemann said, okay, during equilibrium 2 pi FP equal to the threshold voltage. Okay, and it conduct current and so on. So now what happened when we see the VSB is greater than 0? Okay, so when this VSB greater than 0, so there will be a positive what we see here. So positive voltage here. Okay, positive voltage. Okay, so due to this, where is my pen? Okay, due to this positive voltage, so it will be able, so from here you know that P substrate, the majority carrier holes. Okay, when you have positive voltage here, it will actually pushing holes. Okay, pushing holes to this side. Okay, so holes will be pushing away from this region. Okay, due to this, okay, channel is actually much extended further. Okay, so instead of you have this XD portion or the depletion region portion like that. Okay, so now this XD will become extended. Okay, will become extended, and this XD extended is not because of the in Schottky barrier diode you have V reverse, if you still remember, built-in potential, and then you apply V reverse. In here you apply VSB greater than 0. Okay, VSB greater than 0, so the XD will be extended to the XDT. Okay, and due to this also, you will have more charge inside here if you still remember. Okay, so in here, the phi s now, okay, the phi s now, instead of equal to the 2 phi fp, now you have to consider plus VSB. Okay, plus VSB. Okay, in this case, the threshold voltage is no longer equal to the phi fp. Now the threshold voltage is equal to the 2 pi fp plus VSB. Okay, plus VSB. So now you have a new equation for the phi s, which is equal to the phi fp, and you have to include your voltage VSB, which is greater than 0. All right. So this is what happened when we apply substrate bias effect. Okay, this is like a common question usually asked in final exam. Okay, what do you understand on the bias? So you explain in terms of what happened when VSB equal to 0, which is normally happen during equilibrium where phi s equal to 2 pi fp. However, when you apply VSB greater than 0, so this is what happened. Okay, you must be able to explain uh, um, during VSB equal to 0 and during VSB greater than 0, okay, in terms of the energy band diagram. All right, so let's move. Okay, so when you further increase the VSB, of course, this one will be much increased. Okay, so this VSB increasing. Okay, VSB much increase with the VGS increase. So this is what happened. Okay, so the current is the same. However, the shift of the VGS is to depends on if you increase the VGS will be shift to the right. Okay, so due to the XDT, okay, there is a QS. Okay, so now the split charge region QSD equal to 0, QSD max, so it's equal to this equation. I think you still remember. Okay, which is equal to the ENDXDT. Okay, however, when it is VSB greater than 0, now you have to include the portion for complicated the VSB. Okay, however, the chip threshold voltage, okay, the same equation, delta QSD over Cox. Now you have also to include the QSD in the portion of plus VSB, right? Okay, so now, what is the advantage of application substrate bias? Okay, you can also in advanced structure. Okay, in advanced structure, I will have no break. Okay, I think because I think I can finish there. Okay. Is it okay if I no break? I will say okay. How about the rest? Okay. Mm-hmm. Okay, example, the advanced structure like nanotube and also like silicon nanowire. So the structure is no longer the same. Okay, no longer the same. Okay, like normal structure where you have the gate, the source and drain like this, so on. So you have this structure, gate, source and drain. So the structure now for silicon nanowire is a little bit different, okay, where it has carbon nanotube, okay, in between source and drain. Okay, like this. Okay, carbon nanotube is in between source and drain, and the structure is become more complicated because this is the carbon nanotube and the gate is all around. Instead of the gate just on top of the oxide like this, okay, now for carbon nanotube or silicon nanowire or any advanced structures, the gate now is all wrapping around the carbon nanotube. Okay, the carbon nanotube. So this is the example of substrate bias. So you may ask, okay, you can only apply substrate bias effect zero. No substrate bias effect means equal to zero, then you can still measure the current. However, for advanced structure like carbon nanotube and nanowire, you will apply the bias at the substrate. So this substrate, okay, this substrate is not equal to zero. Why? Because it taking advantage in order to become another gate or the alternative for another gate to push to actually create the channel. Okay, so structure like this, the advanced structure like nanotube or nanowire, so actually they use this kind of advantage of the substrate bias effect. Okay, not only they apply gate voltage, okay, not only they apply gate voltage, they also apply the substrate voltage, okay, in order to produce channel very fast and to produce more electron flowing. Okay. Okay, other than that, so although this is not really important, however, I have to still explain. Okay. Okay, so the frequency limitation, okay, MOSFET application usually used in the linear amplifier circuit. Okay, if you look at here, the equivalent model, I think you have familiar with it. Okay, if you still remember, this is the symbol, okay, for the depletion mode. So this is the gate, and this is the drain. Okay, this is the source and bulk. All right. Okay. So the equation, if I think you still remember, okay, during the electronic device circuit, okay, where you have to draw the AC equivalent circuit, which is represented as a small signal equivalent circuit, if you still remember. So when you apply small signal equivalent circuit, if you still remember, you have to include all the internal parameter. What is internal parameter? Is the capacitance. Okay, so since if you still remember, in between this junction it has internal capacitance. So you the small signal equivalent circuit, you have to include all these capacitance. If you still remember, CGD, CGS, and CDS. Right, so where are these capacitance is actually inside the MOSFET structure. So you have CGS, CGD, and then you have CDS, and so on. Okay, not only that, um, on that you also apply internal resistance inside the junction like S and RD. So where does why in AC equivalent circuit, if you still remember, the GM VGS, okay, GM VGS, okay, the equivalent model for GM VGS, if you still remember. So you are drawing like this, right? So this is represented as a GM VGS. If you still remember, so where does the GM coming from? So this is actually what I have explained. Okay, what I have explained in the previous slide. So this is the transconductance inside the channel. Okay, inside the channel. So that's why the equivalent model is coming from here. So this GM is actually the transconductance. Okay, transconductance or the resistivity inside the channel. Okay, so that's why it become GM-BGS. Why GM? Because of the internal transconductance inside the channel. All right, so this is more on the um, AC equivalent circuit. Yeah, so this is what you have learned in the in to electronic and circuit device, the electronic device and circuit. Okay, so you have CGP, so you have this one CGS, CGD. So this is the capacitor. So you have CD, CGS, and also the equivalent model, small signal equivalent model, GMVGS, and so on. All right. So the simplified is at low frequency. CGD and CGS are replaced with open circuit. Okay, and RS and RD is ignored because it is too small. Okay, so that's what you have learned lah. So more on the for low frequency equivalent circuit. Okay, so this is the AC small signal small signal circuit. All right. Okay, so this is it. Okay. And this time, if you still remember, so this is still in small signal circuit. All right, so you have this VGS and then GM VGS, the internal resistance inside the structure. Okay, I think you familiar with it. Okay, you apply KVL to here. That's why you got VGS. If you apply KVL, okay, you got VGS equal to VGS prime. Okay, and then the current here is GM VGS prime plus RS GM VGS prime. Okay, so it is the same equation over here. Okay, finally you will get that GM VGS is equal to this portion. Okay, and ID is equal to GM prime VGS. So this is the small signal circuit. Okay, for the frequency limitation, it has two limitation factors. So first is the channel transit time, and second one is the capacitance charging time. Okay, channel transit time is more on the mu, okay, the mobility, or how fast the electron can pass through inside the channel. So for example, if you assume the electron velocity is equal to the saturation velocity drift, where V saturation 10 to power of 7 cm per second. So if you have channel length 1 micrometer, so the transit time is 10 picosecond. So the maximum frequency that you may get is 100 gigahertz. Okay, so this is the approximation basically. Okay. Okay, so how quickly, so means that this is the mobility, how fast the electron or the carrier, okay, inside here. So how fast this electron can pass through or can move, okay, between source and drain. Okay, so this is so this is the example. Okay, so the saturation voltage is 10 to the power of 7. For example, channel length for 1 micrometer. So this is how fast they estimate that the channel can move. Okay, with 10 to the power of 7 centimeter per second. Okay, so the time taken about 10 picosecond, okay, to flow from source to drain. Okay, so this is the meaning lah. Okay, the meaning. Okay, MOSFET capacitances means there is associated charge time. Of course, when we talk about capacitance, okay, capacitance, of course, you have learned from the MOSCAP. Okay, it is between two plate. Okay, yes, this is the oxide. What happened to my pen? Okay, so of course there is a charge. Okay, this charge. Okay, also depends on time. Okay, also depends on time, how fast this charge can charge and discharge. Okay, depends on time. All right, so other than that, I think this one you also familiar. Okay, the junction here is supposed that to be capacitance in vertical. If you have capacitance in horizontal, you have to split it into two. Okay, so this split, split it, how you split it is by using Miller capacitance. Okay, so now your capacitance has been splitted. Okay, so this one more on to find the current gain. Okay, current gain is equal to the GM over 2 pi F CGST plus CM. So this is for high frequency, okay, for high frequency. Okay, for high frequency application, you have to look on the current gain. Okay, current gain. So current gain is more on the current out over current in. So we know that I out is equal to the drain current. So this is more on the equivalent for the high frequency application. Okay, for high frequency application. So the derivation is the same like what you have learned in the LEC. Okay, so the cutoff frequency is equal to the 2 FT. Okay, if you still remember, you have this. So this is basically your frequency, and this is your gain, if you still remember. So this is your, there is a cutoff frequency over here, like minus 3 dB, if you still remember. So this is your high frequency that the MOSFET can able to reach, and this is the low frequency that MOSFET able to reach. So basically, this is the FT. All right. Summary. Okay, we come to the summary. So for the N channel MOSFET, and P channel MOSFET for enhancement mode has been explained, and also the basic transistor action in modulation and also current drain versus VGS has also been explained. The IV characteristic relation and okay, the phi s equal to the twice phi fp. Okay, however, when you apply substrate bias, phi s now equal to twice phi fp plus vsb. Okay, where you have to consider the substrate bias effect. Okay, small signal equivalent circuit of MOSFET was developed, and various physical factors that affect the frequency. Okay, and expression of the cutoff frequency. All right. So I think I have covered all. Okay, for the MOSFET operation. Okay, basically, what I may say that it depends on how much, how large the electrons. Hello, can you hear me? Hello, hello everyone.
Now we can hear you, ma'am. Yeah, now can.
Since when you didn't hear? Huh?
Just now. For
Just now.
few.
Okay. Already come to summary, right? Oh yeah, my internet connection here not so good because I'm using Wi-Fi. Forgot to connect to LAN. Right, doesn't matter. All right, so basically we have covered everything for the MOSFET operation. Okay, you need to the more on the IV characteristic lah, where it's coming from. Okay, I know that during lab time you just simulate it. Okay, you don't know where does the, when I ask you what is VDS equal to 0, what is linear region, what is saturation region, you don't know. Okay, you don't know, maybe you have forgotten about it. Okay, so at least today covered everything. Okay, for the MOSFET operation. Okay, in terms of the device structure and also the current voltage characteristic and also the transconductance. All right. I think that's all for today. You have any question? Do you have any question? Hello? Can you hear me? Hello?
Yes, can we? Yes, ma'am.
All right. Okay. Any question? Am I cover everything, Kate? So usually what would be asked in this topic is the substrate bias effect, and also um, the frequency limitation. It has two limitation. Okay, the channel transit time and also the capacitance charging time. Not much from here, I think, and basically this lah. So what I may say from this topic, definitely in final exam will be asked this question: what do you understand on the substrate bias effect? Okay, and also transconductance. I think that's all. All right. If you have no question, if you have no question, then surely no question. Can we, I think I can end the class early today. Okay. All right. Okay, everyone. If you have no question, then that's it. That's it for today.
Thank you, madam.
All right. Okay. Okay, all. Bye. All right. Welcome.